In 1983, Air Canada introduced the Boeing 767 to its domestic fleet, the airline's first wide-body designed from the outset for a two-pilot crew, and the first Air Canada aircraft required by regulation to measure fuel in kilograms rather than pounds. Canada was mid-transition to the metric system. Most of the carrier's fleet still ran on imperial units. The 767 was the exception, a single new measurement island in a sea of old conventions. No one had formally rewritten the fueling procedures. No one had explicitly reassigned who was responsible for the fuel calculation on this specific aircraft type. That ambiguity would fly unnoticed for months until the evening of July 23rd. Before Flight 143 departed Montreal for Edmonton, the aircraft's fuel quantity indicating system, the FQIS, was inoperative. A faulty processor had rendered 3 cockpit fuel gauges completely blank. Under the airline's minimum equipment list, the flight could continue if technicians performed manual dripstick measurements and calculated fuel weight by hand. A maintenance worker in Montreal began the process, then was called away. A circuit breaker that should have been pulled to isolate the faulty channel was left in the wrong position. The aircraft was dispatched with blank fuel gauges, relying entirely on a manual calculation that had not yet been fully validated. The Board of Inquiry would later identify this dispatch as a significant cause of the accident. To determine how much fuel the aircraft held, a ground crew member inserted a calibrated dripstick into each tank and read off a volume in liters, 7,682 liters already aboard at Montreal. The next step was to convert that volume to a weight. Jet fuel's density, its specific gravity, does that conversion. The fueling agent handed over a density figure of 1.77. That number was correct, but it was the conversion factor for pounds per liter, not kilograms per liter. The correct figure for kilograms was 0.8000. The 767 needed kilograms. The calculation was done using pounds. The resulting figure, 13,597, was entered into the system as if it were kilograms. It was not, it was pounds. The aircraft already carried roughly half of what the instruments now suggested. Flight 143 stopped in Ottawa before continuing to Edmonton. There, a second dripstick check was performed. Once again, the volume was measured correctly. Once again, the density factor of 1.77 pounds per liter was applied where kilograms per liter was required. The new figure was entered into the flight management computer, 20,400 kilograms of fuel, the computer was told. The actual fuel on board was approximately 9,250 kilograms. The flight required 22,300 kilograms to reach Edmonton. No single individual in this chain had acted recklessly. Each person did what they understood to be their job. But the system had never specified whose job it was to verify the unit of the density figure, and in the gap between responsibilities, the error compounded. Flight 143 climbed to cruising altitude with 69 people aboard, 61 passengers and 8 crew. Captain Robert Pearson, an experienced pilot with an unusual secondary credential, he held a sailplane license and had spent years flying unpowered aircraft. First Officer Maurice Quintal had previously served at a Royal Canadian Air Force base in Gimli, Manitoba, a piece of personal history that would matter before the night was over. The 767 flew westward through clear summer sky. Then, just after 8:30 p.m. Central Time, the cockpit computer began generating an alert. Fuel pressure in the left main tank was dropping. Captain Pearson declared a diversion to Winnipeg, 120 miles away. Minutes later, the right main tank pressure fell as well. At approximately 26,000 feet, the left engine flamed out. The flight management computer, deprived of engine-driven power, shut down. Seconds later, the right engine followed. For the first time in commercial aviation history, a fully loaded wide-body jetliner was an unpowered flight with passengers aboard. The aircraft became, in every functional sense, a glider. Ram air turbine deployed automatically, providing minimal hydraulic and electrical power. The crew lost most instruments. What remained? Airspeed, altitude, a horizon. Captain Pearson had approximately 17 minutes and roughly 65 miles of altitude to convert into distance. He knew gliders. He began to calculate. First Officer Quintal proposed Gimli, the former RCAF station Gimli, where he had once been posted. He knew the runways. He believed it decommissioned and clear. What neither pilot nor the Winnipeg air traffic controller knew was that since Quintal's service days, part of runway 32L had been converted into a drag racing strip. A family day event was underway. Spectators, children, and parked cars occupied the tarmac ahead. Pearson set course for Gimli. He calculated a glide speed of 220 knots. Without flaps and without engine power, the aircraft was descending faster than any 767 had descended before in practice. He was too high on the approach, committed now to a runway he could not see was occupied. Pearson needed to lose altitude rapidly without overshooting the runway. He reached for a technique from his sailplane days. The forward slip, he applied right aileron to bank the aircraft while simultaneously pushing left rudder to keep the nose pointed down the runway. The opposing control inputs created enormous aerodynamic drag, tilting the fuselage sideways to the airflow. It is a maneuver almost never used on large transport jets. It worked. The 767 descended steeply. On touchdown, the nose landing gear, which had been extended by gravity alone and had not locked into position, collapsed as the aircraft settled onto the pavement. The nose scraped the runway for roughly 300 feet, the friction slowing the aircraft before it reached the spectators. Every person on board survived. Minor injuries were recorded among 10 individuals. Canada's Board of Inquiry, chaired by Justice George Lockwood and reporting in April 1985, identified a system failure rather than a single point of human error. The investigation found that Air Canada had not reassigned fueling responsibility when it retired, the flight engineer position on 767 operations. It found inadequate training in metric conversion for both pilots and ground crews. It found that the MEL dispatch with blank fuel gauges was improper. Multiple individuals, maintenance technicians, a fueling agent, both pilots, had each touched a step in the chain. The board recommended that all Air Canada aircraft be converted to a single measurement system, that fueling procedures be made explicit for each aircraft type, and that MEL authorization be tightened. The systemic recommendations mattered more than the individual findings. Air Canada initially disciplined both pilots. Pearson was demoted for 6 months, Quintal suspended for 2 weeks for their role in accepting the dispatch. On appeal, those findings were reviewed and the penalties were reduced. In 1985, the Fédération Aéronautique Internationale awarded Pearson and Quintal its diploma for outstanding airmanship, the first time the award was given for handling an in-flight emergency. Simulator tests conducted after the accident found that multiple other crews attempting the same scenario did not survive it. The aircraft itself, registration C-GON, was repaired and returned to Air Canada service. It flew for the airline until January 2008, 25 years after the night it glided into Gimli, before being retired to the Mojave Desert. The Gimli glider endures as a human factors case study because the error requires no incompetence to explain. Every person in the chain was performing normally. The fueling agent supplied a real density figure. The technicians measured real fuel volumes. The pilots reviewed real numbers. The failure lived in the boundary between them, in the assumption that someone else had verified the unit of measurement, in a transition period where imperial and metric conventions coexisted without a clear handoff protocol. Aviation has since hardened these boundaries: standardized fuel documentation, explicit unit labeling, independent verification steps. The lesson is not that careful people can be careless. It is that systems must be designed as if capable people will, under routine conditions, trust numbers that look reasonable, because they will, and occasionally those numbers will be wrong.